Welcome to Push and Pop. I'm your Shafu, and today's episode is with Tanishk and Vectorized. From Ithaca, we're gonna walk us through the Porto contracts. So Tanishk, Vectorized, thanks for taking the time. Maybe we start with a high-level overview, Tanishk, of what exactly is Porto, what are the Porto contracts or the account contracts, and we start from there.
Nice, yeah. Thanks for having us. Super excited. So for Porto, basically, like the way that I like to think about it is it's like a complete redesign of what accounts look like. So we don't follow 437. We don't follow like any other standard. So we've built from scratch from first principles in an attempt to be minimalistic, to be gas optimized, and to add features that users like modern features that users care about the most. Um, the account itself, like we'll go through the architecture in a sec, but the account itself, I like to think of it as a key store. So we have this fundamental unit of signing, which we call a key, which we'll talk about in a sec. And the account is just like a keychain. And so it's a keychain and it stores your funds. And then it does also like some kind of management of like nonces and other logistical stuff for you. But fundamentally, the account is just a key store. So you can use it for auth, you can use it to hold funds, you can use it for payments, but in the end, it just boils down to managing your keys. So, and we also like, this is not just about accounts. So it's a redesign from the point where the user interacts with the wallet for the first time. So like don't have any extensions. We have this dialog box, which you can see in the demo. You can sign out, sign in using passkeys. So maybe we leave that for another time. We'll focus on the contracts for now. We have three main contracts. The Porto account, which is what holds your funds. The orchestrator is your equivalent of, let's say, the entry point in 4337, but it's just the only role of the orchestrator is to facilitate trustless interactions between this RPC. You can call it the RPC, the relay. Some people call it the filler, the solver, whatever. So this backend sophisticated entity and the user's account, the orchestrator is just a way to like provide trustless access between the two. So the orchestrator ensures that the RPC gets um, paid for the gas that it spends on doing the execution, and the orchestrator also makes sure that if you're paying the RPC, then the actual execution that you wanted to do uh, takes place. And so we can go through the architecture, and one interesting thing that we've done, and like this was vectorized idea in the very beginning, like usually with 4337, a big pain point is this all of these simulation, these state overrides. You don't like people have to talk to different bundlers, different paymasters. We have completely new designs for all of these, like as well. But we've also included an on-chain simulator. So this is like a peripheral utility. You can think of it as a multi-call, but it basically allows you to call a function on the simulator and you get the exact gas numbers instantly. So you don't have to worry about like state overrides as much. You do have to do some simple state overrides, but not like 4337 where you have to do everything for like the balances, invalid signatures, etc. Cool. Yeah. So that's the quick overview. Should we dive into the code or the account now?
Yeah, just to clarify, okay, so the architecture, if you go back, okay, the user interacts with Porto. Porto is basically like a front-end TypeScript library thing.
Yeah.
Goes through the RPC, then comes the orchestrator, and then the Porto account is where the contracts live. The orchestrator is also a set of contracts, and the simulator is as well, right?
Yeah.
Okay,
So all these are the contracts. These three things.
sweet, sweet. And this is all enabled, of course, by 7702. High level overview is I want to create a wallet with a Face ID or Touch ID or whatever, and you never have to touch private keys again, which is super cool.
Ye-
Also turns your EOA to have code, all that great stuff.
Yeah. In
Awesome.
fact, like yeah,
Yeah, go
it's
ahead, go
nice that
ahead.
you mentioned this. It's nice that you mentioned 7702 because like a unique thing about the account is, although we use 7702, so there's this EOA key that you delegate to, we like don't really use any other 7702 features in the sense that as soon as we create an account with 7702, we forget the private key. and we actually delegate the account. So the 7702 delegation goes to this proxy contract. And this proxy contract is just like, if you want, once you forget the private key, you can only do the upgrades through a passkey itself. So we use 7702 because like it's cheap in terms of gas, and you can forget the private key and all of those things. But you could do the exact same thing using like create2 and other things as well.
Interesting. Awesome. Okay, I think that makes sense. Yeah, let's switch over and we take a look at the implementation, at the Solidity code. Vectorize, you want to take over from here?
Okay, wait, keep these on the same screen. So, oh, dang.
Sorry, just give me a sec.
Okay, so I just want to give a bit of a heads up. So there are two things. One is that this Porto account is designed with open ERC standards as much as possible. So in the early phases where 7702 is hyped around Twitter, like the whole of Twitter is like hyping this up like a magical silver bullet. One of the issues I saw is that, okay, maybe MetaMask will have their 7702, maybe Rainbow will have their own. So if everyone use their own delegation, we will create an ecosystem where things are fragmented. So in the long term, we also want this Portal account to be used by like your EOA in your MetaMask, your EOA in your Ruby. We eventually want to have a world where if you want to extend your MetaMask with these features, you can do it. So the first thing I identify is that the execution interface. Basically, every smart account out there, we have some sort of execution interface. And if this execution interface is not standardized, then different front ends might expect different things, and it won't be that simple to do a approve plus swap in one transaction. So the 80% use case we see is that we just want to make approve plus swap into one transaction. And to do that as seamlessly as possible, because everyone wants to create their own stuff, we have to quickly rush out a standard called ERC 7821 to make a very, very minimal execution interface that pretty much everyone can agree to. And I think MetaMask, their delegation is using that in the same ERC 7821 today. So we are also using the same. Yep. So the front end don't need to change anything. If someone has already dedicated to some MetaMask delegation, they can one day swap out for a Porto delegation, and it should just work.
Nice.
Okay. Then the second
Yeah.
thing is this one is a very short comment. The simulator in 437 and any other kind of account abstraction stuff, gas simulation is really a pain. Super pain. So yeah, the simulator contract is you can say it's a bit of a it's ugly but beautiful in a way. Yeah.
Yeah, Vectorize, could you explain why it's so painful?
Okay, so the thing about 437 is that there are all these infamous restrictions on what storage you can read, what opcodes you can use, and if you use a guest opcode, it can only be followed by a static call or a call. This kind of weird restriction, and it's also that during the simulation phase, the aim is so that what is being simulated and what is actually executed on chain will stay as much the same as possible. So that if a relayer simulates that okay, this transaction will pass, then the the actual execution on chain should also pass. Because what if it differs? That means the relayer thinks that okay, this transaction is safe to submit without reverting. But if reverts, then maybe the relayer doesn't get paid in the gas. So all these weird restrictions on opcodes in the traditional 4337, yeah, it's just for that. And in our case, we try to simplify it as much as possible so we don't need to like rewrite the whole simulation in Rust from the ground up. Instead, the relay just calls some RPC, which calls the simulator contract, and then it returns the guess numbers. Yep, so that is the simulator contracts. Oh
Cool.
yeah, actually, a bit of history. Initially, all these are written in pure assembly. So the thing is that okay, we were talking about so these contracts. Tanishk is like a very good high level architecture designer. I'm like kind of a human compiler, so the weird way I write code is like I directly write the assembly because it feels easier for me. But it will make things I would say quite hard to read. And then because this is a very cross-functional team, like there's the Rust guys, there's the JavaScript guys, then if I write in a bit too low level, yeah,
Yeah,
it's the communication through code is a bit bottleneck. Yeah.
yeah, let me give you some history about this. So we used before this, I think at the time when I joined, so vectorize had this execute function, and in this execute function, he had this like complicated assembly block, and like it was like one of the most complicated things I've ever seen. I didn't even like bother to actually dive deep and learn it. I was like, we need to solve this. And he had this for simulate execute, which was never supposed to be called on chain. So there was no need to optimize this. And the Rust guys had to read it because they were actually doing the simulation on the back end. So no one could understand this code except for vectorize. And then we were like, no, we have to normify it. So that's how we ended up with the simulator in the end.
Okay, I see. What about, I know some people have the approach of they have the high level contracts and then they have assembly contracts, which do the same thing, just in an optimized way. You ever thought about going that approach? And basically they test against the same thing, so you can be sure that they're correct, but you have like a high level version for people to read.
Okay, this is the where I go a bit controversial. I would say that 4337 the okay, right now we have some guess benchmark, and I would say a major portion of the savings is from the entry point. We have this orchestrator, which is kind of the entry point in 437, and whenever so it was initially written ground up in assembly, so it's like C instead of writing C port in regular Solidity, you just go directly to the optimal bytecode and then see where you can uh tidy things up to normal Solidity as much as possible without so you establish like a near theoretical baseline on how fast it can be, and then you slowly make things more readable, and until you hit the point where okay, this is good enough. We don't want to worsen the guess anymore. Yeah.
Interesting. Interesting. I think you're the only person I know who does that. So basically, you go from low level to high level instead of the other way, which is very interesting.
Yeah. I think this also gives a bit of so one advantage, although the disadvantage is completely unreadable. One advantage is that sometimes Georgios will ask, okay, can we speed things up? Then we can like say, okay, the theoretical optimum is this. If you do this, yeah, we at most can cut out that much gas. Then Georgios will be okay. Maybe we can spend effort somewhere else better.
Mm, okay. So why the decision in the end to rewrite all of this in high level Solidity? Just because the audits makes it easier to audit?
Okay,
Um,
so yeah, I would say that is one of the things. So auditors are not like they are not gods. Okay, so they are imperfect humans like us. So there will be this thing called auditor fatigue. Like if there's this giant chunk of assembly, it will somehow distract them from focusing on the high level things that may contain bugs. Sometimes the dangerous stuff are the high level stuff. Yeah.
Should we actually look at the simulator implementation and what it does and how it does it?
So I think
Yeah.
yeah, I think Tanishk knows how it works already. He's
Okay.
very more familiar than me.
Yeah. So basically, what we've done is like we've created a primitive function in the orchestrator itself. So it gives you like privileged access, let's say, to the execute function. And you can use, so the simulator contract just calls the simulate function inside the orchestrator. So one of the reasons why we like normified it a lot and we wanted to remove the simulator into a separate contract is that we don't want to be bothered by simulation gas or simulation like security security bugs when you're doing normal execution. So like the simulation will always happen off chain. So and then there's this RPC at the back end which needs like very specific things from the simulator. So like they use simulate v1 logs, so they want to understand the exact gas values. They want to understand the exact payment, the exact payment numbers. When would when does the user have enough payment or not? And then they also want you to have. They also don't want you to revert the whole transaction, because if you revert the whole transaction, then the simulate v1 logs get destroyed. So they want you to maintain they want the whole execution to actually pass. So the one like trick that we've used in general is if at any point like we have to decide, okay, the signature is invalid, but is this a simulation or not? So we have this very simple rule, which is that if the sender's balance, like ETH balance, is the max it could possibly be, like it's the max type U in 256 value, then this means that this is simulation, and you can basically never do this in practice. So yeah, the simulator itself is just a multi-call, and what you'll see it does here is you can't really because executions happen at different call depths, so you can't really mathematically find out the exact gas amount that you have to use for the specific intent itself. So we start off with a number, and then we iterate over that number. Like we keep calling simulate execute with a higher number. So like this combined gas override that you see, this is kind of like the gas that you would like the verification gas offsets and like all of those combined that you would do in ERC 4337. But in our case, like the combined gas is just the total gas that the intent will spend. So it finds a base value and then it iterates over, keeps calling the simulate execute function with a step increase, and then gives you the final amount. And since we've now separated into a peripheral contract, it does not like we can give you very specific features. Like we can give you what step size you want for your combined gas, or there's like this verification offset is because so all chains don't have 7212 yet. So the P256 signatures have a variation of 5 to 10K when you're doing it on the smart contract level. So you can already offset that. And in the end, like it makes it very easy for relays to like give you all of these configurable numbers and then get back like two numbers. So this is the gas used, the combined gas, and then you can use that to just like you'll always be sure that this transaction will go through, and you can configure the steps however you want. So yeah.
Okay, very cool. Cool. Should we switch to the to the actual account contract and take a look what's happening there?
Yep.
Ithaca account, yeah.
Yeah, I guess
Oh,
like one quick thing.
you also renamed this from Porto to Ithaca account, right? Just 30 minutes before this, I saw the PR.
Yeah, that's a good catch. Like I think we might rename the Porto project soon to something else.
Ah, okay.
And we don't want
Okay.
to upgrade the contracts just because we renamed the project to something else. So that's why we call it Ithaca everywhere now.
I see. I see.
Yeah,
Cool. So yeah, let's look at the account contract.
cool. Maybe I'll give a quick overview and then I'll pass it over to Vectorize for all of the juicy assembly stuff. So like I said, we have the account is just a keychain, and we have these four types of keys. this is the 256 SecP 256 R1 key, and then when you put it inside like the WebAuthn standard, you get the pass key. This is the standard Ethereum keys, and then we have this external key, which you can think of as like the 7579 validators, or this basically allows you to. We've created our own interface called the iSigner. So this is if you can create any contract with this interface, and this basically allows you to extend your signature capabilities to any other kind of key type that you want. And one of the examples that we have with this is the multi-sig signer. So you would want to use, like, we think that these three keys mostly cover 80% of the cases that you would ever want to use, but there are some key types which require special configs, like the multi-sig signer needs special configs of who the owners are, what the threshold is. So in that case, it's better to have that in a separate contract, which maintains its own state and doesn't have to like be the state doesn't have to be changed for the contract for the account itself. And then we have this concept of a super admin key. So one thing that we like a lot of the resource lock people struggle with, and we've kind of taken a bold step in not doing, is that this is valid signature. Like we only allow super admin keys. So there's this higher privilege level called the super admin keys, which will give you 1271 compatibility. So like suppose you do a session key, right? And you're worried that the session key will use your approval on the permit to contract to bypass the spend limits, because there's no way that you can enforce spending limits if the call is happening through approve, because the contract itself is never called. The ERC20 is called and the approval is used, but the contract never knows that the approval has been used. So there's no way for us to enforce spend limits in that case, which is the reason why we only allow super admin keys to sign 1271. And if you just want to check the signature, then you can use our internal function. Like it's a public function. You can use this unwrap and validate signature, which is exactly like 1271, but since it's non-standardized, you don't have to worry about 1271 approvals or permit to approvals. And what else? Yeah. So all these like authorize, revoke, spend limits. So we have spend limits inbuilt. All of these functions can only be called by super admin keys. You have to make a self call to approve. You have to make a self call to authorize. So, and only super admin keys can make self calls. So there's two like privileged tiers of keys. Is there anything that you want to add to this, Vectorized?
Hey, okay, so when designing the contracts initially, the idea is to restrict it to just one execute function. This way, when you're scanning through the calls to see whether this session key can call it or not, you only need to focus on one function that is dangerous, which is the execute. For all the other functions, we have a modifier called only this, which means either it must be called by the contract itself, by the EOE itself. Yeah, so all the sensitive stuff, we mark it with only this. Okay, so this somehow makes our, we call it guarded executor logic. Okay, so guarded executor is how we implement two kinds of guards. The first kind of guard is the spend permission guard, which basically says within a certain time window how much ERC20 you can spend, you can pull out from your account using this session key. The second kind of guard is execution guard, which states what contracts can be called, what function selector on the contract can be called, and we allow for wildcards like any contract or any function selector. So these two types of guard, the execution guard and the spend permission guard, they act together so that the whole thing is safe, even with a session key. So, for example, if we are using this Ithaca account on a MetaMask account, which has maybe a few CryptoPunks or Bored Apes, very expensive NFTs, NFTs are not covered by the spend permissions because they are ERC20s only right now. Um, but because of the execution guard, the session key cannot call some contract that has maybe is approved to pull all the NFTs unless it has a execution permission assigned to it. And only super admins can assign permissions. So if you want to create a execution permission, you have to use a super admin key. If you want to create a spend permission, you have to use a super admin key. Okay,
Okay.
so there
Yeah.
is some kind of involved logic down here. It's a bit ugly. The long story short is that there is no one way there is no way to somehow discover on chain all the ERC20s that has been that
Deployed.
that has state related to this account. So the way to do that is that we try to guess whether from the core data whether this is a ERC20 whether this core data deals with some kind of ERC20, and if it does, then we have to check the before and after difference and see whether it will exceed the spend permissions. Yep, so it's quite involved. Basically, the logic is very involved. And all these long comments describe all the intricacies of this spend permission logic.
Interesting. Okay, so which Tanishk, if you scroll up, which functions do you guys check for here? You check for approve, set spend limit, approve. Interesting. Transfer. Okay. Yeah, there's no way around that, I guess.
Yeah.
Damn, the ERC20 standards, huh?
Maybe we should add 6909 or 11. I'm not sure. Okay, so the main use case I see for these spend permissions is subscriptions. For example, I want to approve a session key which is controlled by some kind of third-party app to pull, say, 10 USDC from my account every month. Yeah, I can use this session key with spend permissions.
Okay, interesting. Yeah, it's very okay. Subscription. Hey, you can only take $10 a month out of my wallet, which is basically a spend limit, right?
Yeah.
Yeah.
If you want to do it one time, you can. Right now, you can just use permit to actually. If you want to do it one time, but if you want to do like subscriptions, then you have to use spend permissions.
I see. Cool. Maybe would be interesting to me like to see an end-to-end example and what happens exactly. So let's say I'm signing up through Face ID, for example, right? A user authenticates through Face ID. What's happening exactly in the like what's happening in the contracts exactly? What gets called? What gets executed once I want to do a transaction?
Yeah. So I think maybe it's useful at this point to go through the intent struct to understand like what are the different flows. I mean, the account itself has two execution modes. Like you can see here, if there is a privileged level that is given to the orchestrator, which like ignores some check for gas optimization. And then there is this very simple execute function, which is that you don't have to even go through the orchestrator. You can call execute directly on the account. You can sign something. You can sign these calls with your key, and you can like do any execution you want. But in general, like most of the flows, whatever you'll see through Porto will go through the orchestrator. And if it's going through the orchestrator, then it needs to go as an intent. And this has a bunch of fields. So like the first time that you're creating an account, a Genesis passkey is created for you. The Genesis, so you have an EOA. This is an ephemeral EOA. It only exists within the pop-up itself. The EOA assigns the authorization, and the EOA assigns the execution to authorize your Genesis passkey. After which the private key is forgotten. So on every new chain that you go to, you have to use this passkey. Even to upgrade the account, you have to make a call from the account itself using the passkey to the proxy, which upgrades the account. But let's say your account is now set up, and now you're doing normal flows. And so, does that like answer your questions specifically about how you're doing the passkey authorization stuff, or do you want more detail here?
Yeah, let's go into more detail. The function, what function gets called when, with what auth, and maybe even something like gas sponsoring. How does that work?
Yeah.
Stuff like
Okay.
that.
Right. So again, there's two execution modes. If you're sending the execution yourself, then you just call execute on the account. It goes through this workflow, which checks your nonce. It checks and increments your nonce. It checks and increments your signature. It validates your signature. And if all of that is fine, you execute. I'll come back to this T-stack stuff. It's a little bit more involved. Like, okay, maybe I'll give a TLDR here it is. So you can, when you're outside the account, you can observe that the call is coming from the account using the message.sender, right? But you can't observe which key signed the account. So in some things like the multi-sig signer, an account might have multiple keys inside it, which like multiple multi-sig keys. And how do you know that? How do you do the authorization that the like when you're adding a known or you're increasing or decreasing the threshold for the multi-sig, that the actual correct key or like the correct multi-sig is what authorized the call. So to do that, we have this thing called the T-stack, which basically shows the user, like it's a transient storage slot, which basically shows external observers what key signed the latest execution that is happening in the flow. But yeah, that's just a side quest. Like we can come back to the main flow now. So if you want to do your normal executions without any kind of gas sponsorship or anything else, you just use the simple execute. But the real power and the real features of gas abstraction and all of those come through this flow of the orchestrate. So you create an intent, like this is the execution data, which is what you would put in the standard flow. But there's also other things that you sign over. One is the pair, which is the actual account that is. So this is the paymaster, effectively. We have another way of doing the paymaster, which we can talk about later. But if somebody can pay on your behalf by setting the address as the pair, and then there's this pair signature, payment signature, which gets passed to the pair, and they can verify if they want to pay for you or not. There's the payment token. And so one thing that we have differently from 4337, or maybe not differently, but is that you can specify the payment token in which you want to pay in the intent itself. So this RPC on the back end, it will suggest you a token. So like if you only have USD, it will suggest you the amount of USD that will take. So you can set the payment token here and you can set the payment amount. You might notice these things called the prepayment max amount and the total payment max amount. This is something where we've differed from 4337 a lot, which is 4337 concerns itself a lot with griefing attacks. And to do that, it has like these opcode rules and a bunch of those rules. You can also do it within our design, but one consequence of having this prepayment structure is that you have to refund the gas at the end of the execution. So if I asked for one ETH of prepayment from you, and the gas that it actually cost was half an ETH, so we have to make another transfer to give you back the half ETH. One thing that we noticed is like you kind of in a gas abstracted intent filled world, you don't really need to do this. Like people don't stream like apps don't stream their AWS bills to the user, right? The user asked to do an action, the user is given a price, the user agrees to the price or not. So we don't actually have to do these gas refunds. Like the relay can quote a number and the user can just choose to take that number or not. So we've broken this payment down into two parts, which is prepayment then execute, and then post payment. And then we've given the relay and the user, the RPC and the user, complete control over how they want to um, distribute this. So like if you assume that the user is not going to DOS you because like the user has a reputation built up off chain, or the amount is very small, you're on an L2 where the DOSing like will cost you less than a cent, and you can just blacklist the user. You don't need to have like this complicated refund mechanism and all of that. So in that case, you just set all of the payment as post payment. So like post payment is just total payment minus prepayment. And the good thing about having just the post payment is, one, that you only have to do a single ERC20 transfer. And the second is that you can, the user does not need to have the funds to pay for themselves at the beginning of the execution. So suppose you have like Aave USDC, and so you have AUSDC, your USDC is deposited into Aave. You want to use that USDC to pay for your execution, but the relay won't take your AUSDC because the relay or the RPC does not like know what AUSDC is. In that case, you can include an execution to pull funds from the Aave vault or whatever. And by the end of the execution, you will have USDC in your wallet, and the relay will use that to basically pay for itself. So this is like a big change in the sense that we've given relays, like we've assumed that these relays, bundlers, RPCs are sophisticated entities who can do threat protection for themselves. And if they want, yeah, sure, they can take all of the amount as prepayment. And they can also follow 4337 validation rules where only some opcodes are allowed during the pay phase. But our bet is like that a lot of the people would prefer better UX over it, especially for L2s where this is trivial. And we also have this thing called the pre-calls. And pre-calls are basically a way for you to authorize, revoke, like do key operations before the actual execution happens. So suppose you signed an execution with a passkey, but you're going to a new chain, and on that chain, that passkey has not been authorized yet. You already have this passkey authorization because like you authorize the passkey for multi-chain. But on the new chain, you want to add this authorization within the intent itself. So this is what's called a pre-call. A pre-call is a thing that is executed even before we check if your signature is validated. So you can do only restricted operations. And again, we've left all of these restrictions down to the relay. Like we don't enforce what can go into a pre-call. You can do authorize, revoke, and all of that. But ideally, you would just authorize and revoke keys within a pre-call. And then your verification happens. Then your payment happens. Like prepayment happens or not, depending upon how much you've put in the prepayment max amount. Then you do the execute. Then you do the post payment. So that's kind of the flow.
Very interesting. Cool. Awesome. I think at this point, let's briefly talk about testing. Like, walk me through your testing infrastructure, unit test, fast test, invariant test, all that good stuff. How do you set this up?
Vectorized?
Okay. um. So okay, we heavily base this on a pattern used in Solidity. We call it guided fast testing. Manually guided fast testing. So the idea is that there is a magical function called underscore random, which allows you to generate a stream of random numbers based on based on the fast. You know, when you create a fast test, you just have to include like some parameters. So down here we just put a bytes 32. It means that this is a fast test. And then based on this underscore random function, we can somehow encapsulate different subroutines into their own testing function. So we don't need to worry about how to set up all these accounts every time. And we can reuse the testing code as much as possible. And we do all this complicated fuzzing logic to check, okay, whether this workflow for this path, whether it will trigger anything wrong. For that path, whether you trigger anything wrong. Yeah, so this is how we do our fast testing. invariant testing, yeah, this invariant testing is basically stateful fast testing, and this way of testing essentially simulates invariant testing. The invariant testing as we know it. So,
Yeah,
yep.
cool.
Going
Yeah.
through all this code is like crazy. Seriously. I think the most insane code is the gas simulation testing code. We have to test the gas simulation too, which is freaking crazy.
Yeah, let's look
But
at that. Let's
yeah.
look at that.
So basically we have to create some kind of contract that burns gas in a loop. And then we have to simulate calling this contract at various depths because of this infamous 63 over 64 rule in Ethereum. Okay,
Hmm.
basically what the 63 over 64 rule says that is that if you pass 1000 gas into a static core, it's not actually 1000 gas you are passing. You are passing 63 divided by 64 times 1000. That's the actual amount of gas that can be consumed, can be used by the subcore. So because of this, even if your whole transaction says it takes around 100k gas, the amount of gas you're passing in is not actually just 100k. You have to multiply it by some factor, and this factor cannot be, um, it's not a constant. It depends on how deep are your cores. Maybe the S-Tor is like 5 levels deep. Maybe the S-Tor is like the opcode S-Tor is like 10 levels deep. And depending on how deep the opcode is, you have to pass in different the amount of gas you have to pass into the very top transaction is different because of this 63 or 64 rule. And this crazy test is just to make sure that the simulation works. Dealing with this 63 over 64 rules. Yeah, it's a bit.
Yeah, I think we found the most amount of bugs with this, like these tests, like because they,
Yeah.
yeah.
Oh, that's really cool.
Oh yeah. One trivia. You know when you revert, when you revert, there's the storage that is warm will get unwarm. This is a EVM trivia. Yeah. So we also have to account for all this in our test.
Hmm.
I forgot where it happened, but at some point we actually have to think about. I somehow like figure out why the tests are failing, and it turns out, yeah, that is the subtle thing I missed. I forgot which point in the code it is.
The check for the 6364 rule.
I think okay. Initially, I wrote some reason why I have to revert the transaction, so that okay, so I see. So you know the simulator that is a pass-through mode where it detects the balance equals to U in 256 max. And then there is a revert mode. That means when you run it, it reverts it. Then after that, we submit the transaction in the test again. Yeah, the reason is because if you let the transaction just pass through, then the thing gets warm, and then the second time you hit it, you're actually hitting it with more gas than it actually needs because of the slots are all warm. So we have to make the simulation revert to unwarm the slots so that we can make sure that the transaction still pass even all the slots are cold. This kind of subtle things.
Very interesting. I will
Okay.
definitely.
If you don't get any of it, it's okay because this is such a niche thing that I think 99% of contract devs don't touch in their life. It's such a
Yeah,
niche topic.
that's true. That's true. But yeah, let's. I would be interesting to know about your guys' approach to testing, auditing, and basically getting contracts into production in general. Like, how early do you get auditors involved? What kinds of audits do you like to do? That kind of stuff.
Okay, I say my there's a bit of hot take down here. Okay, so um when I was like coding these contracts, one way I do it is that the low level stuff that we call it business agnostic. That means anyone else can use it. I put it in Solidity for two reasons. One is so that I can do as much fast testing as I need, and all this fast testing will take time. So it's better to have it in the separate CI in Solidity. And second, you can use as much assembly as you want in Solidity, and just assume that just trust that it works. So every time I merge something into mean in Solidity is only after I've marinated and like scrutinize it to the utmost extent. So once the things has been merged into Solidity main, and then we use it in these Porto contracts, you can be quite sure that it is safe. So then you will focus on the high level logic, see whether anything breaks or any vulnerabilities you miss. So one thing I am scared of, okay, in security, uh, okay, in testing, you can only test for stuff that you know. But the scary part is you don't know what you don't know. There may be stuff that you don't know that might happen because your contracts are not used in a vacuum. Those kind of stuff are where we think we need to spend extra paranoia on.
Yeah.
Okay.
Yeah.
Um,
Yeah, Tanishk, yeah. What's your
yeah,
opinion?
I was just talking about like some of the processes that we have now and we're going to implement now. Like right now we're in developer preview, but to move towards production. Um, so we have this bug bounty open, which we're going to like increase over time as we like merge features in because we're still developing features. We kind of don't believe like in regular audits, especially because like some of the work that we've done that we're doing is very niche, very involved. Like you have vectorized assembly that only few people in the world can really accurately audit. So instead of getting like a stamp of approval random audit report, we want to get like good security researchers involved in the process early, like looking at the code, kind of like what UniV4 did. So like they let people marinate for some time with the code base, and now we also have a bug bounty. So that's kind of the approach we're taking, and we might audit things at some point, like when we reach feature freeze. But right now, we want like independent security reviewers who have good experience in the space to be looking at the code one way or the other.
Very interesting. How far away are you guys time-wise from having this in prod?
Um, we've been having like active discussions about it, and also a discussion about what we mean by prod. So like, there's two or three big features that we want to launch soon. So that's interop, like which is going to come next. Cross-chain intent. So basically, everything is chain abstracted, stuff like that. After that, we might want to do sub accounts depending upon if we think that session keys are how safe we think session keys are people actually able to use them properly, because there's this concern with session keys that you just by the function selector you can't really determine what the safety level of that session key is. Like you could apps could ask for session keys for like grant role, grant admin, vote, all of those things like that, and there's no way for you to screen through all of those function selectors. So we are actively thinking about sub accounts. And then we also have like some other features that we want to do, like social recovery, um, maybe privacy at some point. So we're still looking at feedback of when we will reach freeze, feature freeze, but we will not do it in the way like that the contracts are only live once we have all of the features. So we'll keep upgrading the contracts and we'll like keep having these checkpoints where we think that the contract's in production. And I think one of those checkpoints might come very soon, um, in the next couple of months, maybe even earlier.
Nice. Nice, very exciting. Well, awesome guys. This was super interesting. Really cool contracts. I'm gonna take a second look at the testing infrastructure that you have. Yeah, Tanishk, vectorized. Thanks for taking the time. Any links I should point listeners to, except for the GitHub,
Yeah,
of course.
it's just the docs and the GitHub for now. The bug bounty you should take a look at. Just there, but everything is in the docs.
Fantastic. Well, then, yeah, thank you guys. Thank you guys for taking the time.
Yeah, thanks for having us. This is fun.
Thank you very much.
Awesome. Then, guys, thanks for tuning in, and I will see you in the next one. Bye bye.
Okay.